Excellent. All right, so it's my pleasure to welcome you today. We're very pleased to have our own Institute Director here, Yakir Aharonov, and he'll be telling us about some new thoughts about the deeper meaning of quantum mechanics. So we're thrilled to have you, Yakir.
Okay.
Begin.
Well, it's certainly nice to be again in Chapman after 3 years of Corona. Oh, I forgot to switch it on. Can you hear me now?
Yes.
Okay. So, it's good to be here again after 3 years of Corona. It's hopefully to be away. And I'm going to talk to you about some thoughts, I have about quantum mechanics and try to make it more logical. You see, at the beginning of last century, there were two revolutions in physics, relativity and quantum mechanics. Both revolutions revealed a host of new phenomena that was very non-intuitive because they were very different from our everyday experience. Now, in the case of relativity, Einstein was able to do the following: just to accept that the velocity of light is the same for all observers. He was able to do thought experiments that were very logical. You could explain them to guy in the street as long as he knew a little bit of mathematics of high school. You could explain why the time is flowing different rates when you are moving fast, close to the velocity of light. All the other very strange phenomena could be followed logically with common sense, just accepting this axiom that the velocity of light is the same for all observers. So nobody could say that something is really impossible to understand about relativity. We can use just common sense and following the thought experiments of Einstein, and we can develop new intuition that will be relevant for relativity. This is absolutely not the case of quantum mechanics. In quantum mechanics, you have to accept a lot of things that the best you can hope is to show that they are consistent. For example, you have to accept the fact that light is made out of ruptured energy. Nobody explains why. They say it's an experimental effect. Then you can use it. Because of that, you can't know the position momentum because the light must disturb. You try to measure a particle, the light, because it has a minimum energy, must disturb this particle. So you deduce the consistency also that you have uncertainties. But you accept the fact that you have uncertainties as experimental effect. The fact that you have light with photons, you have to accept it as experimental effect. Then you see the strange phenomena of interference. And you say, that means that this particle in quantum mechanics can be not only a particle, but it can also be a wave, just like in the electromagnetic case, the wave was made of particles. But we try to ask yourself, what does it mean that a particle is a wave? Everybody says, look, the most interesting about quantum mechanics is that a single electron can be at the same time at two different locations. And then you ask logically, what does it mean? Can we apply common sense to it? The answer is no. In fact, Feynman said, if you try to understand it, forget about it. If you fall into a big hole, you will never be able to come out of it. Why? Because the electron has a charge and a mass. If you say that the electron is both here and here, we ask, what about the charge and the mass of the electron? Is there the whole charge here and the whole charge there? No way, because then there would be two charges. Maybe there is half the charge here and half the charge there. Then you measure and you find all the charge here. So that half charge that was here must very quickly jump there, and that will cause a lot of currents and mess. So you can't say that the charge is spread when it's a wave. So what is it, this wave? Then you say, we in physics know there is something that's called amplitude. And it's the amplitude that's there and there, but we can't explain to the man in the street what amplitude means. We only have to go through very advanced mathematics and see how that can be relevant for experiment. So there is no simple story that we can tell about quantum mechanics that will make sense the same way that we were able to do in relativity. Now I want to tell you that I believe that it's possible to start quantum mechanics just with one axiom. And the axiom is the dynamics of quantum mechanics is not the Poisson bracket, but is the commutator. Let me tell you what it means. I mean, if you have in classical physics, you describe classical physics in the Hamilton formalism. So you say, I have an Hamiltonian that is p squared over 2m plus d of x in one dimension. And then the Hamilton equation of motion are the s dt is equal to the h dp. That means that in this case it's p over m. And the p dt is equal to minus the h dx, which is equal to the force at the position A. And now, if you have any observable which is a function of x and p, then the FDT is equal to the FDX times the xdt plus the FDP times the PDT, and that is then the FDX times the HDP minus the FDP times the HDX. And that thing is called Poisson bracket. So in classical physics, the time derivative of any observable which is function of x and p is the Poisson bracket between x and p. Now you come to quantum mechanics. And you use the Heisenberg language, not the Schrödinger language, but Heisenberg language. Heisenberg says that if you have any function of p, x and p, that now x and p are going to be operators, the time derivative IH bar times the dt is equal to the commutator between f and h. Commutator rather than Poisson bracket. Now, at first it looks like this is a very small change, because, for example, if the Hamiltonian is p squared over 2m plus d of x, then that equation of motion will tell you still that if you take the time derivative of the x dt, it will still be equal to p over m, even for operator. And the time derivative of p with respect to t for operator will still be equal to minus dx. The time derivative, the derivative of the pdx. So it looks from that point of view that this modification is going to be only small correction of f of h. If you take instead of the x dt, you take the dt of x squared, you're making some correction proportional to h bar, and these are minor corrections. So in fact, I read once a comment by Dirac that said that the basic difference between quantum mechanics and classical physics is not the dynamics, because the difference always has small correction as part of h bar. It's really in the kinematic how you start to describe the state of the particle. You have to describe like a wave function instead of a point. And I claim to differ from Dirac, and I claim actually that in this equation is hidden all the new properties of quantum mechanics. Let me show you one example that anticipates what I'm going to tell later. We know that experimentally, after the work of Planck and later of Einstein, that light of the frequency nu is made out of lumps of energy which are h here. And we ask why. Can you explain why this is the case? Not accepting just as an experimental fact. Is there an axiom that requires that necessary this is the case? And the answer is yes. If we try to solve the equation of motion of Heisenberg, we find that in general it's very difficult to solve this equation. Apart from simple cases like harmonic oscillator in hydrogen atom, when Heisenberg came up with this equation, people found that it's very difficult to try to solve these equations once you have something more complicated than simple harmonic oscillator or simple hydrogen atom. Then came de Broglie and suggested that quantum particles should also behave like waves in analogy to the classical waves that have also particles like behavior of photons. And then when Schrödinger heard about it, he said, I can write an equation, a very wave equation, that will actually describe what a quantum particle does. So, what does it mean then? If I have a vector in Hilbert space that describes a quantum system, and the vector is a function of time, if we know the behavior of this vector, we will know also the solution to this equation. Why? Because if I know a vector in Hilbert space, I can ask the following question. What are the sets of all operators for which this vector is an eigenvector? I call this deterministic operator. It's the opposite question to the usual one. Usual one, you say, if you have a vector psi, you write it as superposition of eigenvectors, and you talk about that superposition. But here we talk not about the eigenvector of psi, but we talk about the set of all operators for which psi is an eigenvector. You can measure these operators without disturbing the particle at all, because if this is an eigenvector, if you measure it, you find exactly the same psi is an eigenvector, and you did not change it. It was an eigenvector, if there is no degeneracy, and it's still an eigenvector. Now it turns out that if you look at the set of all deterministic operators, that set has the following property. That first of all, it takes the sum of two deterministic operators. That sum is also a deterministic operator, because if psi is an eigenset of that, and psi is an eigenset of that, it's an eigenset of also the sum. It's even true for the product. If you take the product AN plus AN to make it Hermitian, then you apply it to psi, and you still get it in the product of AM times AN, right? You apply first AN, you get A times psi, and then this will give the product. So this set of deterministic operators is a closed set under this both algebraic operation. Now I claim that if you know the set of all deterministic operators, there is only unique psi. Let me show you an example. Suppose I just look at a very simple vector space of 3 dimensions. And I look at a vector 1, 0, 0. The set of all operators are Hermitian matrices of 3 by 3, right? These are all the operators that can act on this state. The question is, which set of these operators will leave this unchanged? And you can see that if the operator has 0 here, 0 here, 0 here, and 0 here, and any entrance here, that will leave its state unchanged, right? But if you know all these operators, that's the only vector that will be unchanged. Any other vector will be changed. That means that if we follow the behavior of the deterministic operator, we know exactly what happened to the vector. And we can follow it by measuring without disturbance at all. So the idea of the Heidelberg picture is that in order to see the time evolution of psi, you can do it by just looking at the set of deterministic operators, see how they develop as a function of time, then you will know exactly what is the state of the system. So we can now follow the state of the system without collapse, without uncertainty, as long as you can solve the Heisenberg expression of motion. But it turns out that it's very difficult. Then came Schrödinger and say, look, if I write psi of t as an integral of coefficient x and t times eigenstate of x dx, then in order to find the behavior of psi, it's enough to know what is the equation of motion of this coefficient. And it turns out because the Hamiltonian is p squared over 2m plus d of x, it's very simple to solve this equation in that representation. So, because it was so simple to solve this equation, even in 3 dimensions, everybody left Heisenberg. Heisenberg came with his idea a few months before Schrödinger. And before Schrödinger, everybody was trying to solve the Heisenberg equation of motion for more complicated atoms. They found this very, very difficult. Then when Schrödinger came with this equation, everybody left Einstein, everybody started to calculate all the interesting problems in quantum mechanics using the Schrödinger equation. And because of that, everybody believed that this is really the way to describe the quantum physics. But this is a mistake. There's a way to solve what happened to psi of t, and from that to calculate the deterministic operator. Why? Because there is no experiment we can do on a single particle that will tell us what are these coefficients. Right? For example, I can take 2 different coefficients whose integral is not orthogonal. Then there is no way on a single particle to measure all these numbers. So although these numbers have very much to solve that equation, they cannot be considered as a physical picture because they are not property of a single particle, while the Heidelberg operators are property of a single particle. Therefore, if we want to talk about single particle, we should develop intuition what happened to this operator, and not mathematical intuition what happened to this guy. We have very nice mathematical intuition, but that doesn't help us to really think deeply what the physics means. This is the important thing. So I want to give you now some examples. The first example is, following the dynamics, can we prove, thus having a dynamic law, that light must be quantized, namely that there must be photons. Up to now, we accepted it only as an axiom, an experimental effect, something we must start with, but that's not true. Because if we have any periodic system, for example, we look at a vector that describes light of a given frequency. So we know that the one property of that light is that if you change t, if you start at psi at time 0, we describe the state of this mode of light. And you now apply to it e to the minus I ht over h bar, that will give you psi of t. That follows from dynamics. Now, if psi is a periodic system, that means that after time t that's equal to 1 over nu, the system must come back to itself. Any mode of light that has a frequency nu, doesn't matter what its amplitude is, after a period t equals to 1 over nu, it must come back to the same state. That means that e to the minus IHT times psi 0 is 3 is equal to 1 over nu, then e to the minus I ht over h bar times psi of 0 must be equal to some phase times psi of 0. Because we know that after time t come back to the same state after the phase. What does it mean? It means that this operator into the minus I et over h bar, where E is the energy, this operator must be equal to the state into the I phi. What does it tell us about the energy? It doesn't tell us what the energy is, but it tells us that the energy modulo h over t. If we set the energy by multiples of h over t, that thing doesn't change. So it tells us that the energy of the modular energy must be known. And the modular energy tells you that the last energy of this mode must be integer times h nu plus whatever the energy is the ground state, which is this space t. So here is an example that I use dynamic in order to conclude something that up to now was supposed to be an experimental testimony. This is a glaring example that that's the information that you have a periodic behavior of a system, tells you that it must be made out of quantum lack of energy, and that's why we have photons. So photons are not experimental fact. They follow from the dynamics. This is one example of what I want to be able to show in a lecture of 5 hours, all the consequences. But I gave you already one nice example. Is there any question about this thing? Because it's so important.
Unfortunately, I have 4 hours, Yakir. You have 4, so.
Okay. Now, so if we look back at the difference between Poisson brackets is equal to the GDP and the FDP times the DDX, or we look at the quantum analogous equation f of p times g of x, where these are operators, and we say that commutator has to be equal to 0, and we want this to be equal to 0. If we want the Poisson bracket to be equal to 0, we think the only way is that one of them is a constant. So only three-way solution. Because if the product of this is equal to 0, either this is 0 or this is 0. So there is no trivial solution to this question: can I find the function of p and the function of x whose Poisson bracket is equal to 0? They don't exist. On the other hand, if I calculate that thing, it turns out that if f of p is equal to f of p plus p0, and g of x is equal to g of x plus x0, and if x0 times p0 is equal to multiples times h, then these two things commute. How can I see that? If f of p plus p0 if f of p is periodic, then I can write f of p as the sum of an e to the I pn of p0 times n. I can fully transform it in this way if it's periodic, right? Now, each one of those is a translation operator. So when I look at this commutator, when I write it like this, it changes x by x plus nl, so nx0. So therefore, if g of x is periodic, then, and this is periodic, then these two things commute. So then this is a very interesting fundamental difference between the commutators and the Poisson bracket. And it says that in quantum mechanics, this type of modular variable plays a very important role. We saw one example when we look at the time evolution of a periodic system. This was an exponential or modulo thing, and we saw that that's exactly. So we are very familiar with the modulo variable with respect to time, e to the minus LC, because this is its time evolution. But this tells also that it's going to be important to look what is the meaning of this commutator. And let me tell you what is the meaning of this. If we look at the basic new facts of quantum mechanics, which is interference. So I want to discuss it in one dimension. I have a superposition of wave packets here and wave packets here with no overlap between them. This wave packet moves in this direction. This wave packet moves in that direction. When they meet, we see interference pattern, and then they separate it again. Now, if I ask what is the set of deterministic operator for that superposition, that deterministic operator must distinguish between psi1 plus psi2 and psi1 minus psi2, for example, because these are orthogonal states. It turns out that if I write any function of operator p of x that I can expand in power series is to the n times p to the m, then any operator like this will not be able to distinguish between this plus z and this minus z, because that operator includes only functions of x that knows locally and at most n derivative. And all the derivative of this function still don't overlap that one, so the average of any operator like this cannot depend whether this plus z or this minus z. Therefore, the deterministic operator for this thing cannot be expressed as the powers of polynomials that are powers. On the other hand, if I look at the operator into the IPL, that operator, if that distance is L, when I multiply it by this, it takes it's a distance L. And how do I know that? I cannot do it by expansion in powers of P, because that expansion, if I write this as P to the N, L to the N, over N factorial, sum is this, supposing this is the same as that. That is true only for analytic functions. If I apply that thing, that each one of these separately to this, it will never overlap with that. But if I apply the sum, it is overlapping. That means that I have to have a proof that the sum is acting as a translation operator that doesn't rely on the Taylor expansion. And the way that I do it is by saying that if I have, if the set is psi of x, I know that I can also write that vector in Hilbert space as an integral of phi of p times p dp, where phi of p is the Fourier form of this. Now, when I apply any function of p on any set of p, it gives me a number, definitely, even though, so from this I can prove that that thing translates this by L, even though I have a non-realistic function. So it turns out that for the description of interference by deterministic operators, we must use things that involve the modular momentum. Now, we wrote an article, I think that the earlier was in where we say how to make sense of the two-Swiss experiment. Because up to now, as far as I understand, even if anyone tried to understand what happened in the interference experiment, we have the following problem. If we look at our superposition of two weights, and they meet and they give this weight can be written as e to the minus x plus L over t squared divided by delta squared times e to the I k0x, where k0 is the average velocity of this, and k0 is very large compared to the uncertainty of the momentum. So this wave will move essentially changing its position without changing its shape from the time, because the spread is proportional to the uncertainty in momentum, and the distance covered is proportional to the average momentum, so I can cover a long distance before I have to worry about the spread. So if I start this one, and this one is equal minus x minus L square over delta square, and this is minus I k0x. So by the time they meet, both of them will have e to the minus x square over delta square, and it will be the sum of these two, which is cosine k0x. So I see an interference pattern when they meet. Interference pattern where I have, for example, a position where it's 0. On the other hand, if I start with a single wave packet, either here or here, of course I will never get a 0. So that's why everybody concludes that the particle must be in both wave packets, because there is no other way to explain it, according to the general belief. But that's not true, because it's possible that I know that the particle is here, and also I know that it has a deterministic, another property, which is the deterministic of momentum. And that it can explain why, for example, if the particle here and I put the potential here, the interference pattern will be shifted. Up to now, everybody thought that this must imply that the particle must also be here to fill the potential. Or in 2-3 experiments, if the particle only goes here, how does it know whether this field is open or not? But the hydrogen picture tells us the particle can go here and still have another property, which is this modular momentum, whose equation of motion depends not locally on this. And therefore, there is a new way to think about all the properties of quantum systems, not to think about the Schrödinger picture, which is misleading, because the Schrödinger picture tells at the same time the particle moves here and here, and there is no way to understand it logically, or by common sense. But we can understand, like, in the time of Newton, before Maxwell, we thought about interactions that are not local. If we have a charge here and charge here, we say, trivially, that charge gives force of this, proportional to 1 over r squared. Nobody thought that this is strange. Only when people came to relativity and causality, they said, there must be some messengers to explain locally what happened. Those messengers move not faster than the velocity of light, so that particle will feel that thing only much later, after time L over c. But that is due to causality, and now we say that there is a new possibility that if we look at quantum mechanics and we have uncertainties, we can have a situation that something will affect something else non-locally, but we will not be able to observe it because that thing that is affected, like the modular momentum, is completely uncertain. So the change of it cannot be seen. But if we look at pre and post selection, we look how it's possible to find somebody in which we know which particles were on one side, then we can conclude the particle was on one side, and nevertheless it showed the interference pattern. So I show you how, when you start believing that the real intuition should come about by looking at the Heisenberg operator, and looking at the Schrödinger picture only as a method of helping us to solve what the Heisenberg operators are. Because if we know how the vector in Hilbert space evolves in it as a function of time, we know that, we know what are all the deterministic operators. So we know, if we know the solution, we know how the deterministic operators evolve as a function of time. So we know how to check what happened to the whole system just by looking at undisturbed measurement. the uncertainties don't enter into it all. But to solve it is very difficult if we try to solve it by looking at the Heisenberg equation of motion. So we are looking for a simpler way to solve it. And that is what's given by the Schrödinger equation. But then the psi of x is like potential. Potential help us to formulate, for example, electromagnetic theory in a nicer way, but it doesn't mean that because of that the potential are real. So the psi of x is not a real description what happened to a quantum system. It's just a mathematical aid to find what the Heisenberg operators do. This is my method. Okay? Now, what do you gain by thinking correctly about quantum mechanics? So let's show you an example from my own life. At the time when I was still just immediately after my PhD, I was a fresh assistant professor at Yeshiva University. And at that time, everybody thought that if you make a measurement of the system and make a collapse, that collapse erases the possibility of the future telling us what was the past. Because, for example, if I have a particle that starts with sigma z equal to 1, and then I measure and find the particle with sigma x equals to 1, I can still predict what will happen in every measurement in the future. But knowing this, I cannot tell whether I came in the past from sigma z equal to plus 1 or sigma z equal to minus 1. That means that if you believe in collapse, it destroys the time inversibility. That's what everybody believed at the time I started to think about it. But then it occurred to me that if you try to find the boundary condition in a time-symmetric way, namely, you start at time t1 and you make a measurement and find the vector psi 1. And then at time t2, you make a measurement and find the vector psi 2. Now you can use both boundary conditions and ask what can we tell about the present between the two. And it turns out that that restores the time reversibility. Why? Suppose I ask what happened if I have a Hermitian operator A that has a complete set of eigenstates state A n alpha n, where alpha n tells you that A has an eigenvalue alpha. So we ask another question. Suppose at the present I make a measurement of A, and I find one of the eigenvalue vectors. And ask now, what is the probability to start with psi 1, find that vector in the middle time alpha n, and then find the final state psi 2? How do I calculate it in the usual picture? I say, from here to here, I have the vector psi 2 that involves a function of time from t1 to the time t. So I start with the time evolution operator times psi of t1, and that brings me to the present, right? The time evolution is equal to minus IHC minus t1. Now I want to find the state alpha n. So I take the scalar product of that thing, that gives me amplitude. But if I square it, it will give me the probability to find alpha n. So now I say, okay, from now on, I have alpha n propagating as a function of time. So I have to take now the knowledge that I have the vector alpha n propagated from the time t to the time t2 and projected from psi 2. This will give me now amplitude to start with psi time t1, get in the middle alpha n, and end up with psi 2. So the absolute value of this square gives me what is the probability to find in the middle alpha n if I know these two boundary conditions, right? Now, I do a trivial mathematical change. If I call this thing, say, C of alpha n, absolute value of this will give me the probability. I can write the same C of alpha n in a new way by doing the following. I start with psi with T1, take U T1t, multiplied by alpha n, and then take alpha n here. And instead of applying the U here, I apply U dagger. So I write here U dagger of T2 times psi 2 and multiply this way. So for this, I have to take psi 2 this way. Yeah. So what this tells me is I have a new picture. I start with psi 2, psi 1, and work it until the intermediate time this way. I end up with psi 2, and I take it as a graph propagating back up to here, and I calculate just by scalar product, using both of them with equal footing, what is the result of the thing in the middle. Let's show you now that it's a covariant picture, because I can interchange the time, it will still be the same story of this coming from the past and this coming back from the future. The scalar product will be the same as before. So this restores the time symmetry. And we wrote an article. I came at that time, Bergman, who was assistant of Einstein, was part-time at Yeshiva University, and Leibovitz, who is a very well-known professor in statistical physics. I told them about my idea, and of course they wrote the article for me, as usually. And this is the formulation that's called the ABN formalism. So the ABN, Aharonov, Bergman, Leibovitz, is exactly this formalism where we use the two vectors of equal footing, okay, instead of just one vector. Now, the advantage of this mathematically is glaring, because if I use this picture, for each different alpha n, I have to solve the Schrödinger equation, how alpha n evolves as a function of time. It's a complicated differential equation, and I have for each different alpha n solve a different differential equation. Here, once and for all, I only calculate that time evolution, one differential equation, and then the rest is just scalar product, which is trivial. So just from this mathematical point of view, this formalism has a big advantage on the other formalism. That was the state of affairs for maybe 30 or 40 years. And then I started to think about it again. And I said the following. If I have, this is time, I take the simplest quantum system, and I start with sigma x equal to 1, and at time, that's at time t1, at time t2, I find sigma y equal to 1. And now, what do I say about the time in between? In the one vector picture, I say, here it was only sigma x equal to 1, that's the only thing I knew, and only from then on, it will be sigma y equal to 1. That's of course assuming that the spin is a constant of motion. But in this new picture, I say, no, actually, this vector goes back in time, this vector goes forward in time, and the present has two information. The information that sigma x is equal to 1, and also the information that sigma y is equal to 1. So I started to think, is there any way that I can do suggest an experiment that will show that in the time in between, both sigma x is equal to 1 and sigma y is equal to 1. How can I do it? Well, once I evaluate, I say if I measure sigma x, of course I get 1 because it's the same as before. If I measure sigma y, I get 1 and minus 1. But I throw away the cases of minus 1 because I only look at this case. So sigma x and sigma y are known, but that's trivial. Because really, sigma y wasn't known here. It was both cases plus 1 minus 1. The fact that I decided not to look at the case where -1 doesn't mean that it wasn't really with half probability +1 -1. So that's not the way to show that both of them are there. So then I have to ask the question, what happens if I measure sigma x plus sigma y? Aha, this must be 1, this must be 1, so I should get here the value 2. But that's impossible, because if I divide it by square root of 2, then the spin component is 45 degrees. And that can be either 1 or -1, not square root of 2. So, the best time I got pricing, my picture led me to the wrong result. I thought that I should get the value square root of 2, and it's impossible to get it. But I started to think carefully what's going on here. So I'm saying the following. Here I have sigma x going this way, here I have sigma y going this way. And during this short period of time, I want to measure sigma equals sigma y. But when I try to put a device that measures sigma equals sigma y, that device necessarily, like a certain experiment, rotate this one by a certain amount and rotate this one by a certain amount. So this measurement necessarily destroys exactly the information that I wanted to have. So I started to think maybe if I will make a measurement that is very, very weak, that it doesn't disturb any of them, then perhaps I will see the value square root of 2. That's how the idea of weak measurement was born. And indeed I checked, if I do a very, very weak experiment, namely that I have a measuring device, this is the wave function of the pointer, and the difference between sigma x equals sigma y is equal to square root of minus square root 2 is a very, very small shift. So in one experiment, I cannot tell anything. But if I repeat this experiment on n particles and look only at the measuring devices, and I have n measuring devices, look only at the measuring devices that the particles added in this thing, it's about half of them. Then for this measuring device, I see that the sum of the momentum really was shifted by square root of 2 times each one of them, times the epsilon of the measuring device. Now, here is a very important point. People usually think that because you do a very weak measurement, you get only very weak information about each system. But that is not true. Think in classical physics, when you try to measure the charge of the particle, the way you do it, you have to take another charge here and see what acceleration does it have. And it's a function of the relative position. But if this charge is big, then the experiment lasts a finite time, that charge disturbs this charge, and therefore I will not see it in a given position. So then I use the idea of a test charge, very, very small charge that will not disturb this thing, and it will still tell me what this is if I repeat this experiment many times, and I get exactly the same signal. So you know, if you have a noise, and you have a signal you have a radio that sends a signal, and the signal is much weaker than the noise of the wave. So if you have only one time that signal, you will not tell anything. So if a pilot wants to send a signal where it is, he has to repeat the signal many, many times. So the edge of the addition of this signal in the n times is proportional to n, but the noise grows the square root of n. So eventually, even though in each individual case you could not see it, from the whole thing, you reduce it in each triangle of this signal, even though you could not tell by measuring. So weak measurement doesn't mean that you measure only very small information about each particle. If you collect all of them, then you say that although for each one I got very, very weak signal, like in the case of test particles, for all of them together, I can deduce that each one of them gave me this value, even though there was if I look at the sum of all the momentum for the measuring devices, it's first of 2 times n times epsilon. Epsilon is very small. But if n is very large, I say that the change of the total momentum of all the measuring device divided by epsilon gives me what each one of them was. And therefore, it is not true that in brief measurement you only measure something very, very unknown. I mean, you have a new reality in the time in between, and that reality is really there, but you can find it only if you don't disturb it. So you have to do measurement that don't disturb this reality. Once you do that, you find a new beautiful reality. And once I discovered this with measurement, a whole kind of new phenomena suddenly appeared. There was a phenomena that we call quantum Cheshire effect. There was a phenomena that was now called superoscillation. There are many experiments that use the fact that the rift value that we measure is the psi to 8 psi 1 divided by psi to psi 1. If psi to psi 1 is very small, we can get much bigger values than the maximum allowed value. So like here, the square root of 2 is bigger than the allowed value of 1 and minus 1. So the idea then is if you learn to tell the true story about a mathematical theory, like the case of quantum mechanics, then this new theory can help you to think of new type of experiment. You see, when we have a mathematical formulation like Schrödinger equation, this is supposed to be a universal theory. That mathematics doesn't tell us which interesting question to ask it. We can ask any question, then the mathematics will solve it for us. But which interesting question to ask, it will never tell us. So we must develop some way to see the mathematics in a story that will help us to think what interesting new experiment we want, new question we want to ask the mathematics. And this is a beautiful example. The thing could have been discovered 100 years ago when quantum mechanics was developed. But it wasn't discovered because nobody told the interesting story. If we tell the story of the two vectors, then we can ask this interesting question, what happens when we measure sigma x plus sigma y? So my lesson is the following. I was not able to show you all the way I can start with the Heisenberg picture, and from this develop intuition about everything. I get only a glimpse of some examples. And the most important thing that I haven't mentioned yet is because the Heisenberg equation of motion, the Heisenberg dynamic, allows us to put boundary condition in the future and boundary condition in the past, and we say that the boundary condition in the future affects the present. But how does it consistent with free will? If at the present I can do a measurement that will tell me which experiment is going to be in the future, that is a violation of causality, and causality is like free will. Because once I find what the measurement theory is, I can change my mind and not measure sigma y at the end. So if I could show in a single experiment that this equals the square root of 2, this would be violation of causality, and if I couldn't have free will, I would be forced to measure sigma y at the end in order to get this result. But if I can only deduce the thing in hindsight after I measured here and know in which cases I got sigma y equal to plus 1, then I go back and look at those cases and I see indeed there was a change there of square root of 2. So at the present, this information from the future is hidden by uncertainties. And only when I do the right postulation later, the thing comes out. So the answer is that if God wanted that the future will affect the present, it must have been also make sure that the theory has uncertainties. So uncertainties are not an axiom. They follow from causality and from the fact that the future can affect the present. Only when you have uncertainties, that could happen. Because if you didn't have uncertainty, you wouldn't be able to have free will. Okay, this is what I can tell you in 1 hour. Thank you very much. If anyone has a question. Yes.
I have a question. I'm sure everyone else would understand it, but one thing for me is when I see the time one and time two,
Yeah.
it makes me think of, an EPR paradox where you've got one position and another position.
Yeah.
And when you're doing that, when you're studying that and you're doing the Bell inequality, one of the things you do is you say, I don't know what measurement I'm going to make over here until this measurement's been made. I don't even know what I'm going to do, and then I change it a little bit,
Exactly. Right.
and you get the Bell inequality.
Right.
And so I'm wondering, could the same thing happen here, where you've got your time one, you know what you're going to measure, and then what you're going to measure at time two, you don't know until you've made the middle measurement.
No.
You don't even know what you're going to do until you've made the middle measurement, and then you make the final measurement.
Well, I always formulate it slightly different. If I do the measurements in the middle, if I find an answer that is impossible unless I do something in the future, that is not the case of the EPR. Because in the case of EPR, any measurement that you do there doesn't force you to do any particular measurement here. If you do an EPR of 2 spins, and then if you measure here the spin for example, the spin of sigma x for each one of them, it doesn't force you to measure here sigma x. But if you measure sigma x all of them, that guy will know what result you will get. So the EPR doesn't tell you that if you make a measurement there, you are forced to have a particular measurement here. But here, if we measure in the middle, and we start with sigma x and all of them have sigma x equals to 1. Then in the middle, we make measurement and we find all of them equal to square root of 2. That could only happen if at the end I would measure sigma y for all of them and find 1 there. Otherwise it couldn't happen. But I can change my mind and not measure sigma y. As an EPI can do this. If an EPI, instead of measuring sigma x there, I measure sigma y, it will be completely uncertain. Because it's about sigma x. So here, there's something new. So I am saying that if I want to have the possibility of having that impossible value and still not violate causality, it should be made, this should be hidden for me until I make the final measurement and postulate the subend where I go to sigma y equal to +1. So I'm saying now the following. People say that if you start with ensemble that all of them are sigma x equals to +1, in some cases, if you measure sigma y, you get +1, in some cases you get -1. So I'm saying instead that really there was a difference between the two particles. The difference was already here, but I can find the difference only by a future experiment. So I have then a new picture of saying that really I have here each particle described by 2 vectors, and then a history vector which tells me what was the result in the past, and a destiny vector which is a vector that is propagated by the Hamiltonian will end up in that state. And these 2 vectors describe together the weak reality. But that doesn't get weak reality, and let's take that this vector knew already, quotation mark, what I'm going to do experiment later, but it cannot tell me about it, then I still have the possibility of free will. And that is the explanation of the famous sentence, all is known, but permission is given. Okay? Then people try to understand how can we have free will and be responsible for our deeds if God knows in advance what we are going to do. Okay? So here, the party knows in advance what we are going to do later, but it can't tell us about it. And because it can't tell us about it, we are still free to change our mind, and therefore the belief that particle was different. Okay, it's very deep, but that's what I can say now.
Okay.
Thank you. Any question? No? Yes.
What's the progress on reconciling this with general relativity?
Both are practically relativity. Now,
That's a lot.
but the hope is that if you understand quantum mechanics better, there is some hope, but it hasn't happened yet. But I can tell you another thing, that using, that I'm going to discuss that with Daniele this afternoon, using super oscillation, I can have a new model for the start of the universe with avoids quantum gravity. But I can't say more now. Any other questions?
I'm going to check the chat to see
Oh,
if
yes.
people on the Zoom call have any
Okay.
questions. So if you're on the Zoom and like to ask a question, I'll check the chat here. No chats. Okay.
Okay.
They're stunned.
We're stunned.
All right, thank you very much.
Okay.
There's food, by the way.
What?
Lunch, sugar lunch.
Yeah.
Freelance?